Hi, I'm David Bader, and I direct the Institute for Data Science at the New Jersey Institute of Technology. I'm very pleased to introduce today's distinguished data science speaker. We have Gordon Bell, who is a Microsoft researcher emeritus. In 1960, Gordon joined an early computing company, the Digital Equipment Corporation, or more commonly known as DEC, where he spent 23 years and became the vice president of R&D, responsible for the first mini and time-sharing computers and DEC's VAX. In fact, he designed the I/O subsystem of the PDP-1. He was an architect of the PDP-4 and the PDP-6, and he contributed to the PDP-5 and PDP-11. I'm actually very grateful to Gordon for that last machine because the very first computer I programmed in 1972 was a PDP-1145. After retiring from DEC in 1983, Gordon founded the Encore Computer Company that produced one of the first shared memory multiprocessors. In 1987, as the National Science Foundation's first assistant director for computing, called SCIES, he led the National Research and Education Network panel, also known as NREN, that became the internet that we know as we know it today. In 1987, Gordon established the Gordon Bell Prize to recognize the extraordinary efforts to exploit modern, highly parallel computers. Gordon maintains three interests: the evolution and use of computers, technology-based startup companies, and life logging. He is a fellow of the American Academy of Arts and Sciences, a fellow of the ACM, and a fellow of the IEEE, and he's a member of the National Academy of Engineering, of the National Academy of Science, and the Australia Academy of Technological Sciences and Engineering. Gordon received the 1991 National Medal of Technology by President George H.W. Bush. He was also the first recipient of the IEEE John von Neumann Medal in 1992. Gordon's also received numerous other awards, including the Vladimir Karapetov Outstanding Technical Achievement Award of Eta Kappa Nu, and he was also named an Eta Kappa Nu Eminent Member in 2007. Gordon is a founding trustee of the Computer History Museum in Mountain View, California, and today, Gordon Bell will be speaking to us on ExaScale more than I ever imagined.
This is a very, very personal talk. It's kind of my perspective about these massive change that's that we've undergone for the last 60 years, and it's one that sort of I can't even imagine continued changes at this rate. And in fact, any change, even a decade forward, 1,000 time X scale, which is what one might predict, is just unimaginable. But anyway, let's see. Anyway, this is really 6 decades of, I'll say, having a part of scientific computing, mostly at supercomputer level, but always involved with. I've always been involved in supercomputers to some extent. Some of the topics I'm going to talk about today really start a little bit about Moore's law. I've got a model that says, how did we get here, starting from always trying to build the ideal computer and what technology has done to make that possible. And then some of the problems, right? Now is really this question of capability versus capacity computing. So supercomputers are capability machines. That is, you're trying to get the most possible performance you can. on my side, I've always been interested in capacity, namely get as much computing to as many people as possible. So I worked on the sort of cost performance area, sort of less performance and a lot less cost to enable wider use. What I think when I think about anybody involved with these computers today, I'll say the modern clustered computers today, the multiple distributed computers that we operate with presents a collection of interesting problems in parallelism. So your first principles of working with them, I think, is understanding all of the various forms of parallelism that you have to deal with. You know, it's kind of probably the easiest maybe if you can, it's fine to do things that are embarrassingly parallel. So if you have work to do, it's okay to do a lot of the jobs in parallel as opposed to trying to do a single job very fast, because you find that challenge of how much parallelism is inherent in the work that you're doing. So essentially, for all of you involved in this is an era you have anyone working in these domains, I think, with that has anything to do with coding, you have a special badge that totally separates you apart from the ordinary computer science view of the world, which is a single thread of computation. I'm going to try to break this 60 years of experience into sort of three periods. One being really what I would call the Cray Era, and that is really where we're really doing a single thread of computation, and for a particular thread of computation, it's a single thread of Fortran. So it could also be called the era of the Fortran machine. And that's, to me, that's a mono memory computer. That is, we've gotten performance, but basically the performance by speeding up the clock, having a single shared memory, and then putting as much processing elements into the access that memory as the architectures have evolved. And mostly those architectures were evolved by Seymour Cray and the Cray Computer Company. Then there's a period here that I was involved in various ways, which was, to me, it was a very interesting period. It was a period of searching. We were looking for the path to a higher performance. We knew that, in fact, it had to be parallel in some way, because the clocks were bottoming out or topping out in speed. So the question is, how do you arrange processing elements or processors or in some way to get this incredible parallelism? And then in that process, you end up having to, you also, as a byproduct, get another property that it's called scalability. So, whatever you choose, it needs to be scalable, because you need to, as you add as much money as you want to spend, that tells you how much computing you're going to be able to do. That was a period that really lasted a decade. From I mark 83 to 93, and I'll show you how I mark those periods as a kind of a amateur historian. I worry about who's first and where did the ideas come from. So this is a clear era of searching, and there was in fact 50 companies lost their lives in that search trying to build scalable parallel machines of some sort. And then finally, out of that era comes the cluster or multi-computer era or scalable computer era of whatever, taking arbitrary computers, the fastest that you can make, fastest, cheapest that you can make is nodes, and then simply replicating those nodes and tying them together with this fastest network or the best network that you can buy or afford. And now it clearly we've switched to from an era where programming was a simple Fortran job, single thread Fortran job, to it's all up to the programmer now. How do you manage to get all of these computational elements going concurrently? And the number of those elements now are up in the 10 millions. So at least, if you project another decade or so, that would require at least maybe 100 billion, or if you were going to simply get performance by the way we have in the past. Not clear that that's where we want to do, because there are other elements, other people trying different things, such as quantum computing. Anyway, here's a picture of the performance measured in gigaflops, and then so it starts at a megaflop there, and in sort of 1960, and so a megaflop computers were almost at a megaflop in with the first higher performance scientific computer, and then those really that whole set of lines there is one of Seymour Cray and Cray research, as they went from a scalar machine to a pipeline machine to vector operations to multiple vector operations, and that required some fancy compilers, but basically it was still executing the challenge was single threaded Fortran program. And then here we've got all of the machines that we're doing now that are cluster based, and then we're kind of in 2020 we do hit an exaflop, or about half an exaflop in 2020 with the Fujitsu machine. And then so the talk is more talk is going to be about here, this overlap, and here as we proceed on there. In a way, I started out when I was writing a paper about the history of supercomputing. I said, really, you're after the ideal supercomputer. What is the ideal? That's an ideal, assuming you don't have to work about very much about any explicit parallelism, and that is that it's speed, memory, and parallelism all scale indefinitely. So the clock keeps going forever. And then you have a single large memory that you are free to allocate any way you want. And then that was the formula in that first era. So people first started, oh, well, if we have a memory, we're memory bound, let's overlap the memories. And then let's overlap and do prefetch and do some fairly fancy collecting of instructions so that we can execute them if the dynamics of the topology of the program allows. And then and that morphed into the need for the doing of pipelining, so that you have a number of stages and you allocate the various parts of an instruction or several instructions to the pipeline. And then I'd say the big breakthrough in architecture to me was Cray's vector, using vector processing, so that's you just make the operations bigger. Instead of a scalar, you do a vector. And then we do multiprocessors, and then from an efficiency standpoint, you try to do multi-streaming or multi-threading so that you get more out of the hardware. So that was kind of that first era. And then we found out, well, oh, the clock doesn't scale. It's bound now at a few gigahertz. And so that says, well, we've got to replicate the whole computer. And now, once you replicate the whole computer, then of course you don't have one large single memory, and we're now stuck with essentially reiterating the whole cycle again of generating these parallel units within a single memory system. But then the challenge now is how do you map a problem or an algorithm across all of those separate dispersed memories. And then as we're evolving, we're finding, well, try to do things like, well, maybe put the algorithm in FPGAs, or let's build special hardware for all of that. And that's kind of the history of how I see things have moved. This is another cut at the inside, and that is one of that I have to credit Ken Wilson, who was a Nobel Prize winner, introduced us to in 1986 when I came to the National Science Foundation's form size. And he observed that science has proceeded from experimental to a theory-based models or modeling or explanations to one of using computers to do simulation. So that simulation was just a way of building the physical unit, but building that physical unit in software. And then I was also lucky to be there in a lab with Jim Gray and Microsoft lab here in San Francisco in 007, when Gray said there's a fourth paradigm, and that is one of discovery through data. And so I'm delighted to speak at here today to find here you are totally an institute that is discovery through data driven and data science. And so it's been I'd say around a decade since somebody handed me a card that said they were a data scientist. This was not Australian. And so I think data science as a declared scientist is only a decade old. This is Jim's slides from 2007, and so he made those observations of this progression from theory to or from experimentation to theory to one of simulation, and then on now through data science, and he did that remarkably well with the astronomical data, and showed the number of discoveries you could make directly from the data as they organized the data for what is called the Worldwide Telescope, which is you can go and use a telescope and look at any of the celestial bodies in various frequency domains. So Jim really was a kind of a pioneer of naming this as a fourth paradigm. And in fact, I convinced Microsoft Research to edit a book on the fourth paradigm. And let me heard if you all of you are working in data science, this is a great book that has about 60 examples of people doing of data science that was going on at the and it's part of the developing theory and body of knowledge about dealing with that. I had to put some, I want to just say about the irony of how long these paradigms take to discover, and that was in '87. We saw that. I heard this model by Ken Wilson, and then I was at a party or sort of one of these meetings, and the head of the director of science for the DOE rushed up to me and said, "We've got a really new model about what we're all doing, and it's called the third paradigm of science." So a decade later, DOE discovered that they were pioneering the third paradigm. And in reality, I go back and I say, well, actually, wasn't that exactly what was being done in Los Alamos with all those IBM card machines when they were calculating models of what was going to happen when you with the hydrodynamics if you set off a big blast. So anyway, ideas travel fast, or in the order of a decade or two to get something. And I had an argument with one of the computer scientists about this notion of paradigms, and they couldn't believe that there was something. He said, "There's only computing." But that has to be separating calculating from discovery through data. Now, talk about paradigms. When I saw a really interesting set of slides or talk by David, and that's the idea of objects and patterns or structures, and classifying the data you deal with in terms of whether you know what the structure is going to be like that you're looking for, and whether you know what the objects are that you're trying to have in a database. So classical database is you know what the rows and columns are, and then he proceeded to describe these other forms of databases where you don't the objects are unknown and the patterns that you're looking for within there are also unknown. If I go back to kind of the importance of supercomputing, I think I've got to say the most important one has got to be this graph that at least I think I saw probably, I don't know, maybe early 2000 or so, that was by the head of NCAR, and from then on I could never spend much time arguing about whether computing was man-made or whether climate change was man-made. And then one thing I almost came to blows with a computer person, actually a Unix computer, one of the developers of Unix, about whether computing was man-made. And he says, "How can you believe that?" And I said, "You, as a computer scientist, you have to. This is, I believe the computer. This is what it's all about. This model, you have to believe this model and this." And so I base my faith totally on a computer. So climate to me is one of not beyond religion, but if it is a religion, it's computer science as a religion. This is an early model of a SIMD computer that Richardson proposed basically a century ago, and that was you have all these people sitting in this global theater, probably like the globe, and then doing calculations. They're all passing information back and forth and up and down on command. So it was a SIMD computer with people. This was kind of the latest when I drew that line through it. When are we going to hit 2000, or I'm sorry, 2 degrees centigrade? Not sure. That the interesting thing about that is what does it really, what does a degree or so mean in all of that? As far as I can tell, every half a degree or so, there's some new form of disaster that takes place, whether it's ice melting or whatever. And then, so the weather climate prediction is a kind of a good indicator of performance. And this says this is a graph of the time it takes to calculate a 36 hour or 72 hour a weather forecast. And basically it's every 15 years, it looks like you gain a factor of 2 in forecastability. And then one of the other great things beyond long range or weather forecasting is the ability to predict hurricanes, and that has similar kind of effects that have improved. So these are real measures that we get. And then lying at the bottom of the sort of this pyramid of performance, or maybe it's at the top of the apex of it, is this graph or these graphs of what's happening to chips, and the problem here is this middle line is the frequency of maximum frequency. And so we find that in sort of begin in 2000, we had started hitting the gigahertz level, and chips are just moving around between between 1 and 3 gigahertz from a clock speed. And then to counteract that speed, then when one tries to put more cores or more operations on a single chip, so you you're using parallelism by essentially having multiprocessors on that single substrate. And then this top line is the total number of transistors in the chip, and so on. So that's kind of the constraint that everybody's now working under to deal with. If you want to know how much to get a number of ops, you have to first start with, well, I can only get 2 or 3 billion operations in a second. So now, given that, if I want to do X's, why I just have to divide by this by the 2 or 3. So an exa, you got 10 to the 18th you're trying to do. So, and I can only do say 2 billion operations per second. So that says I'm stuck with a half a billion fold parallelism that I got to deal with. And then the other thing that's kind of constrained is that as things are powered, you are kind of power limited, and people now have been stuck in the about maximum of 10,000, 7,000, 10,000 interconnected computers. And then now within that, you then have to get as many operations going within that computer as possible. So there are a bunch of ways. We go back to the standard ways that we do that, including GPUs, and then now there's a kind of a fad going about, well, let's, which has always been there, and that is, can you afford to make specialized chips for particular kind of app, particular workloads? And as you get, particularly in the current AI mania, where people are trying to doing so many of the operations are spent doing machine learning or forming these networks of parameters for in a neural network fashion, that there's lots of opportunities for parallelism, and then lots of opportunities for specialization, and given the vast amount of data that people are using for the training the AI models, why it pays to have a special chips. And Google has done that very much with their TPU chip. The alternative is actually one that Microsoft uses is FPGAs. And so essentially you take the computation and unroll. It's kind of like unrolling a loop, and spread that computation into a pipeline, and make that all available for a flow. And then the other thing you can do is, well, don't compute so many bits if you can. And so if you can, in the case of the neural nets, 8 or 16 bits may be enough for forming those parameters. And then one of the things that I just read about was there's an NSF grant for engineer for basically architecting or collecting all of these various kinds of different heterogeneous computers together, and hope that something good will come out of that, the thinking about that, just by specialization. And they want to try and may have an architecture that kind of puts this hodgepodge of machines together, and presumably that something good happens. I have to mention the fact that the other way to get performance is if you can find the algorithm that says you don't have to do that operation, or that you can, or once you have the memory, you can share it with something else. And then, so that's how you get real speed up, is by the algorithms. And there's some examples. By the way, I'm going to go through these more slides that I probably should have had, but on the other hand, I'm assuming that you can. These slides are all available, and you can look at them. So these are 3 particular slides from Jack Dongarra about arguing that algorithms are as good as hardware speed up any day. Anyway, now I'm going to go back to the sort of 1, 2, 3 eras and talk about the eras themselves. And this was sort of the beginning. They called it a supercomputer. And the first machines really aimed this way were started in 1955 in the kind of the heat of the Cold War, when Los Alamos and Livermore were bound by needing higher performance machine. And this is, by the way, this is the first supercomputer that I saw. And this was at Livermore, and it was sometime in 1962 or 3. And it was the Livermore Lark, and it had a couple of processors, and it also used a decimal arithmetic, and then a particularly high-speed transistor at the time. And so it came out, and it was introduced in 60, so I saw it somewhere, or a little bit later, maybe 61 or 62. And then this was a picture here I think is important because we hear of this Sid Fernbach Award. Sid was the director of Livermore's computing, and there he is on the left. I recall seeing him there, and he always sort of wore sandals and very often had a cigar. And then the man on the right there is Edward Teller. So Edward, he's the father of the H-bomb, hydrogen bomb, and he was at Livermore. And incidentally, I gave a talk there 6 years ago, and I had the honor of having lunch with several Livermore heads in his office that had been preserved there. The other effort was IBM Stretch, and that was a machine that was built for Los Alamos. And So these were comparable machines. And then sort of in there, by the way, was, you see, these were all sort of wired logic. So this is one processor, a single processor. And then what kind of my favorite machine for a different reason that was a 48-bit scientific calculator was the Manchester Atlas, or the Atlas computer that was made by Ferranti, and its main claim was it was the first machine to have a one-level store, so that basically the idea of virtual memory was there. And then the other thing that was important in 1960 was Fortran came out and was pretty much adopted almost immediately as the language for scientific computing. So that made it easy for Seymour Cray, because he now had a target. So from then on, it was clear that he just was building Fortran machines. And he did that very well. His first machine was a 6600, and in there on the lower right cabinet, there's a refrigeration unit, and in each of those cabinets there was a refrigeration unit, and the refrigerator went and cooled various plates that held the modules. And the thing in front is the sort of console that ran that. And if you look at, here was the form of parallelism that began to happen, and that array of 10 computers on the left was a form of multi-threading. So a single-threaded, a multi-threaded machine with 10 threads, and they had 10 processors for I/O. And then on the right was the main calculator, and that was 60-bit word, and then it had an array of elements there, for floating point, several floating point units. All of these units could be operated in parallel or as much. So they were formed out, and we did a sort of magnificent job with a scoreboard to keep track of all that. And then this is interesting because at that very same year, we introduced a machine, a PDP-6, for time sharing. And when I read the manual, the 6600, by the way, this is one of our computers was used as the switch for the Livermore, to get various Livermore computers to exchange data. And the picture here is all of us who were involved. So it was the circuit designer. We had, I think, 2 circuit designers, mechanical, 1 or 2 mechanical engineers, and there were 3 people working on software, and about several technicians there, my secretary on the left, and that was the whole crew that built this machine, 36-bit word and so on. My reaction when I saw the Cray machine or the 6600 was basically, holy shit, how did they do that? And it was a 4-phase, 1 microsecond clock. So that was, I'm sorry, 4-phase, 10 megahertz clock. So that tells you how much parallelism you can expect out of this circuitry. Not very much. And then in digging deeper, the bottom line is, well, Cray put together 600,000 transistors, whereas our six really had only 5,000 transistors for doing timeshare. So it was a timeshare computer that we could handle near 64 users simultaneously. And then Cray then proceeded to do his machine for the 7600, which is basically a 6600, but with full pipelining. In the same period, Amdahl described Amdahl's law as he argued that 2 or 3 different ways of having parallel units were all doomed because of the computation was limited by the slow part or by the synchronization. There were lots of things going. There were 3 other efforts for trying to build parallel machines at the time, and that was Iliad 4 was a particular big, grand one, which had actually 256 processing units, and DARPA funded a quarter of it, 64, and it was here it is. Here's one processing element of Iliad 4 at the Computer History Museum. The gadget in the front part is I think a 5 or 10 megabyte disk, so every processing element had a disk, parallel disk associated with it, and then the processing element there is in the background, and then there was a control element. So all the processing elements executed the same instruction and did them at once, and that was, I'd say, a challenge for parallelism. And then by 1975, Cray sort of took over, and that was said, let's use vectors instead of scalars as our fundamental element. So we can know how to stream and store these blocks of data. If you look inside that stuff, what Cray called the love seat was, you can see these massive power supplies that fed the various bays of logic there. And then if you look at the architecture, everything is really a collection of registers or vectors. And so those vectors were all what you call an operation out that was pipelined and could go fast. This is going into this sort of this controversial era, and this era of search, call it the search era. And this was, it started out with in 82. I have to credit the Caltech Cosmic Cube as probably the first here, and that was a multi-computer with 8 and then 64 independent computers, and they were able to program that to do useful work. And that was key. It started off Intel and 2 or 3 other companies that used that same formula for parallelism. A year before was, I'll say, a really important event, and that was Japan had declared the 5th generation project, and they actually directed at AI, and that really stimulated so much further effort. And then in 84, NSF established the supercomputing centers program through another report. I'll go over these again. And then the end of this era was in 93. So it's the 10-year era of, and I say 93, why it stopped, why it ended, the era ended was that in 93, the CM5, the thinking machine CM5 ran a program. Actually, they ran the first TOPS 5 program. They won the first TOPS 5 challenge, and it exceeded the performance of the Cray vector processor, vector processor that was being introduced. So it really took everybody and said, "Well, that's it. We're over." Whoops! Oh my God! I just looked at the time. Sorry. Anyway, anyway, that triggered all of these efforts, and then particularly the effort at the National Science Foundation, and that's when I joined this National Science Foundation, and Alan Karp had proposed $100 for a factor of 200 in parallelism. So Alan tends to lament what that I went up to him a bit there, but I said, okay, I'll offer $1,000, but I'll give it every year, and we'll do it for a decade. And what we're going to do is measure parallelism. And so that was established in '87, and it's been going on for over 30 years. So it measures it rewards people writing programs. The first group that got that was a trio at Sandia, and on an N-cube, and that was Gustafson and Montre and Benner, and then that became known as Gustafson. Basically said, if the way you thwart Amdahl's law is that you just make the problem, you need to make the problem much bigger. So the can cover the synchronization. This is a picture of a computer that I had worked on for calcula for capability, and that, or for capacity, and that was, you give everybody their own little supercomputer, and this was was actually in a decade after it was about Cray 1 performance, and it was done with 4 processors. And this is the machine that ended that search era, and that was 60 gigaflops in the first top 500, and it made Cray abandon their plan. In the same time period, I switched my allegiance from a shared memory allegiance to the fact that it had to be scalable, and that I was no longer bound by having everything single memory. In the same era, the other important events were MPI, and then also Beowulf. And then here's one that David was involved in that was just a little bit later, 1999, and that was the first, it was at the University of New Mexico, and the first machine to be on the net, the first cluster machine to be on the net. And then at the end of this period, was marked by the fact that there were all these companies tried and failed to make useful computers. Anyway, so these are the 3 events that I claim were the starter events for today's what I would call modern computing is clustered computing, and we have all the events that have preceded that, and then gone on to I think today's more big one is to me the Fujitsu machine that is we'll do an exa-op at the if the ops are a little bit are not 64 bits. And anyway, and then there was a number of other machines. These are some of the other machines that are come to me. This was a particular effort that won a Gordon Bell Prize, and that was actually this machine here, the Sunway in 2016, a Chinese machine that then was able to be used for modeling for a total climate model, sort of the ocean and ice, and then the atmosphere and land as 4 components. And then on the other side, these are some of the people involved dealing with the algorithms, the architecture, and the application. So massive program, to me, a very impressive one. This is a bunch of the, this is on the, if I look at the Gordon Bell Prize, and this is the trajectory of winners of that. So it's both, it tracks the TOPS 500 or track the 500 track the machines there. So it's, but the prize really was for people in programs exploiting the whatever's there versus the recognition of the computers, which is the TOPS 500 number. Anyway, what's going on now is the ExaScale computing program, and it's really a very large effort aimed at apps and expanding all of that. So I'm over time, and I'm sorry, but let me turn it over back to David.
Gordon, thank you very much for such an impressive talk with such perspective. We don't often get a speaker able to give us the last 60 years of computing. And I want to encourage those who want to stick around to use the chat in Zoom to ask your questions. But maybe, Gordon, I can start with one. And as I see your talk, it's clear that the US really led the invention and the leadership in computing for so many decades. Although we've seen a couple surprises from Japan, including the Fugaku machine today that Satoshi Matsuoka has stood up at Riken, which is nearly half an exaflop. And we see the Chinese building domestic, expected to be ExaScale supercomputers this year or next. What are your thoughts about the US leadership? And is this something now that the US has lost its capability, or do you think the US has some more things up its sleeve?
Well, it looks to me like the machines that are sort of coming online, I guess, at Argonne and at Oak Ridge, I think, are in that up in that same performance band. They appear to be in that that level. You know, the U.S. you know goes in and out of of leadership, and you know, the surprise to me, one of the big surprises was the Chinese came from nowhere and then they had sort of 5 years of kind of leadership, and Japan is sort of has its they do they focus on a excuse me. Yeah, my dog didn't want to hear the rest of it, but no, the Japan seems to focus every 7 years or so. I haven't looked at the period, but they have come up with machines that are successful for a couple of years. The weather machine, for example, the weather machine, and there was the other machine at
The Earth simulator.
the Earth simulator, and then before that there was the weather or the wind tunnel. And
Right.
then I think there've been a couple, but they really focused. You know, it's whereas we've got two or three, we've got kind of really two competitors now, IBM versus versus Cray or HP. It's now HP, but because you kind of need that competitive thing, and that's by the way, was the theme that Livermore and Los Alamos in a sense were set up in that way for competing efforts, and being able to choose alternative, being able to look at alternative paths, because you have that. So the question is sort of how do you get that essentially parallelism in the architecture exploratory way.
So there's a question that's come in from Jorge Aponte Gomez that says there was a meeting with a Spanish scientist that talked about cell supremacy, very similar to quantum supremacy. Do you see a future in biological systems that can compute similar to the ones that you described?
Well, it's, I've sort of been in some of the experiments are amazing that, would you ever have a DNA as the storage media? And, right now I think, I'm as a sort of a silicon person, it was like, I can't really, it doesn't seem like it's, the protein is sort of flabby we kind of think of it that way, and cannot possibly have the storage capability that and I don't think they have any calculus. I think what it will do will be more, the more you understand that, the more that will be useful in terms of sensors of other things. So I think it'll be biology will manifest itself in a different domain versus storage, but people are trying the storage stuff.
So on this seminar, we have a number of early students coming from data science and computer science. And I know that throughout your career, you've worked on algorithms, architectures, applications, and more. Is there any advice that you would give a student as to what you think are the most interesting things to work on in the next decade?
I'm not sure about the interesting. I think the important thing now is that you're you really are a pioneer in sort of the fundamentals of what you're dealing with. And the fundamental way it's kind of, these are mechanical fundamentals. These are not the intellectual stuff. They're probably not as intellectual as you would want to claim, but because if you look at all of these computers, they are so damn ad hoc. They appear to, it's amazing to me. And that's why I love being able to reward people for programming them. How you can keep, you can see all these things that operationally, you can see that the ops are there, but it's how do you get data flowing through all that. So it's really the math. I'd say it's going to take, a couple of years of sort of honing a skill. So as a student, I think you do as much variety as you can, as quickly as you can, because these are all these techniques, because things will be more technique oriented than we'd like it to be. I mean, as opposed to intellectual, deep intellectual, they're deeply skill-based. There's going to be a lot of that, and because to me, I look at it as a totally different world of computing from from classical computer science that people are trained in. And in fact, a story at the NSF was I said, we were going to work on parallelism. This was before, I did the Bell Prize stuff, but it was, I'd say our focus has to be on that, because I sort of didn't see computer science as being, to me, that interesting. I saw parallelism being a different set of challenge and a whole bunch of both techniques and theory, and how do you and just dealing with it. And I know Richard Karp sort of said, you can't tell us what to work on. And then Ken Thompson was, no, you shouldn't be doing that. And then also Don Knuth said, oh, that's, he also weighed in on, I can't even write a good sequential program. How can you ask us to work on parallelism? So I had 3 votes for not working on parallel, or not asking people to work on parallelism. And then I think in the end, my AD at the time showed me a little card. He said, in the end, people will go where the researchers will go where their interest lies, and then he said, and their interest really lies where the money is. And so we use the money grants to sort of start to move people, but it was very slow and very hostile in 1987 of people working on scientific computing. And then now I don't know, I would assume that data science has gone through some of the turmoil, because it's now kind of a, again, I think a decade since I first saw a card with data scientists on it, but and certainly Jim Gray really had that feeling in 2007 and sort of kicked some of the thinking along. And so I'm glad you folks are working in that area. Right now, I think everybody's probably rushing to build models to do whatever they can with neural nets. And frankly, by the way, that PDP-6 was one of the first programs one of the people had written, I think after we had I think we had Lisp running on it, and they were running so we ran ELIZA on that. And I look at what a lot of some of these GPT does and some of the applications, and it reminds me a little bit of ELIZA. That it's a modern version of ELIZA. It's truly magic that this thing is talking to you, but it certainly has no idea that I can tell what it thinks it's saying. But anyway.
Well, I do remember typing ELIZA in from a Byte magazine in the late 70s into a PDP 1170. So that brings back memories.
Yeah.
I think we have time for one last question, and it's coming from Luca Capoletti. And the question is, Luca works on high performance graph processing, and we're starting to look into FPGA solutions to try to scale in some very specific use cases. Do you know some labs to look into doing that type of work?
No, no, I'm sorry, I'm not. I don't feel like I'm close enough to
Okay.
Yeah.
So again, Gordon, thank you again for giving this seminar at New Jersey Institute of Technology. I really appreciate your time and all of your wisdom looking at the past decades of computing and where we're headed in the future. And again, I hope that we are able to see each other face to face in the upcoming months and years. So thank you again.
Okay, good. It was a pleasure. Thank you.
Bye-bye.